Okay, thanks, Shiva. Yeah, good afternoon to you all. I would like to thank the organizers, Shiva and Anita, for inviting me here to give me this special opportunity to speak before you. It's a great opportunity for me to speak before you, and what I'm supposed to give is some kind of a popular science talk, isn't it? So what I've started with, I think, is your first day worksheet, isn't it? So why have I started with this? No worries. I just wanted to focus on one of the questions here. It's the last question. Okay, this extra credit question. And not only that, I wanted to focus on this sets and finite sets, countable sets or uncountable. So that's kind of the focus of my talk today. So I thought that, and since this has already been discussed in your classes, in your worksheets, so why not bring it up from there? You have seen finite sets, countable sets, uncountable sets. Are there any other kind of things there? Are there any other kind of sizes of sets? What do you think? So what is an example of a finite set? Yeah. What is an example of a countable set? Sure. An example of uncountable set? Real numbers. You all know why the real numbers are uncountable? Any? Okay. Anyway, we will discuss it. So are there any, what do you think? So these are all kinds of sets that we have, or are there more kinds of sets? So all of you think? Huh? Sorry? These are the only kind of size? Okay. So let's see whether you are right or maybe wrong. We'll see in this talk, and that's why I named this talk A Road to the Infinities and some topics in set theory. And I would like to acknowledge an ESLI course of Benedict, and I won't even try to pronounce this name because that was the inspiration for this talk of mine. So in this talk, what we will talk about are two heroes of set theory, which you might not have heard yet. These heroes are cardinal numbers and ordinal numbers. Okay, what are they? The cardinal numbers, they kind of measure the size of infinity. And you already have that. There can be two kinds. We already have that. At least we know two kinds of infinities. One is the countable infinity and the other is the uncountable infinity. And we these numbers compare the sizes of the infinite sets. And what are ordinal numbers? They kind of relate more to counting beyond infinity. In our last lecture, we saw a lot of counting, meaning adding and counting of natural numbers by kids and also by us ourselves. In this lecture, we'll see a bit of counting beyond that, counting beyond infinity, counting beyond natural numbers. We'll see how it progresses. Interestingly, we have that like this countable infinity and uncountable infinity. We see there are naturals, there are reals. So we have examples of this countable and uncountable infinity. But interestingly, until 19th century, the scenario was not so clear. Still then, infinity was considered to be a pretty problematic concept. So let's go a bit into the history. Okay, how far? So let's talk about the Achilles and the tortoise. So from the around the B.C. Christ era. So the argument says it is impossible for Achilles to overtake the tortoise when pursuing it. Why? For in fact, it is necessary what is to overtake something before overtaking it, first reach the limit from which what is fleeing set forth. In the time in which what is pursuing arrives at this, what is fleeing will advance a certain interval. And in the time again in which what is pursuing will traverse this interval, which what is being fleeing advanced. In this time again, what is fleeing will traverse some amount, and so on and so forth. So this is famously known as Zeno's paradox, Xenophilia, Zeno's paradox. Okay, so what is happening here? He would never reach. So that's the idea. So if you're hearing of it for the first time, please think of what is the problem here, why, is it really a paradox or is it not? Please think about it later. Okay, from Achilles and the tortoise, from Zeno, let's go to Aristotle. What does he say in his Physica book 3, chapter 6? For generally the infinite has this mode of existence. One thing is always being taken after another, and each thing that is taken is always finite, but always different. For the fact that the process of dividing never comes to an end ensures that this activity exists potentially, but not that the infinite exists separately. So he kind of differentiates the notions of potential infinity and actual infinity. And according to him, actual infinity doesn't really exist. It's only the concept of potential infinity. And of course, that's what is according to Aristotle. So there's a lot of history. We have started from B.C., but let's straight move to 19th century. Okay, so of lack of time, let's straight move into 19th century and look into Bernard Bolzano's work, The Paradoxes of Infinity, or Paradoxien, the Unendlichen. So in here, this was actually published posthumously in around 1851. So what he says that, it's interesting, see, not every magnitude that is a sum of infinitely many finite magnitudes is itself infinite. But a remarkable relationship between two infinite sets, that it is possible to pair each object of the first set to one of the second, such that every object in the two sets has a unique partner, which means there is exactly one kind of infinity. It's still going on from that. Aristotle also thought that there's this only kind of potential infinity and nothing else. And then even in the middle part of the 19th century, that concept that there is one infinity and that was still there. And in this situation can occur even if one of the sets is a proper subset of the other. Okay. Now comes your Cantor, okay, the father of the modern day set theory. So he was the one who introduced these notions of cardinal numbers and ordinal numbers. These cardinal numbers was first introduced in his paper of 1874, this German paper, and this which talks about real algebraic numbers. And this ordinal numbers was introduced even before that in this paper of 1872. Okay, so with that we held on the era of starting of the study of set theory. So how did it go? In general, the historically set theory basically started off as a branch of mathematics and studying the infinite sets and its relationship. But subsequently, it also had another role to play in mathematics, which it gives rise to some kind of a foundation of mathematics, which is also known as the standard foundations of mathematics. And these are a few people who contributed to that side of set theory as foundations of mathematics: Zermelo-Frankel's column, von Neumann. These are a few people who contributed. And they developed something called as axiomatic set theory. What are those axioms of sets? They are some of them are very intuitive, like the union axiom. What are those? These are for any sets x and y, there is a set denoted x union y containing all elements of x and all elements of y. Then, even given a set and a property, there exists a set of all elements of that set satisfying that property. This is known as the separation axiom. And in that's how they developed the sets, and then they have it they had it as a foundation of whole of mathematics. Again, there is a lot of history of this set theory developing as a foundation of mathematics, but that's for another day. As I started earlier, the talk for today is looking into the infinities, but I just wanted to give you a flavor of this other part of the other contributions in the set theory as well during that time. And another axiom that is added to this Zermelo-Frankel set theory is the choice axiom, which is known as the ZF plus AC, which is generally termed as ZFC. What is this choice axiom? It says that for every family A of non-empty sets, there is a choice function f such that Fa belongs to A in that family of sets. So given any finite family of finite sets is easy to kind of think of, like let's say 1, 2, and 3, 4. Of course, you can have a function that this goes to 1 and this goes to 3. That function, let's say this is A, this is B. If A is equal to 1, of course, you can think of such a function. But this axiom says that for any family of any kind of non-empty sets, there exists such a choice function. Why am I mentioning it separately? What is the importance of this axiom? The importance is there that even though it results in very intuitive results in mathematics, for example, every infinite set has a countable subset. Pretty natural. Every infinite set would have a countable subset. That can be proved using axiom of choice. You have studied vector space in your linear algebra course. Every vector space has a basis. That is also, that the proof of this theorem is also uses axiom of choice. But assuming axiom of choice can also lead to some very unintuitive phenomena. An example of that is the Banach-Tarski Paradox. What is that? It says that the ball of radius 1 can be, by axiom of choice, decomposed into 5 pieces. Using those sets, one can, using rotations and translations, form 2 balls of radius 1. So you break up one ball and you actually can make 2 balls of the same volume. So you can also prove such results using axiom of choice. So you see there is something interesting to do with axiom of choice. Once again, that's a story for another day. So with this small introduction to set theory, axiom of choice, some axioms of sets, let us now go deep into our main topic, which is that measuring the infinites. Okay. Now, there are many infinite sets in mathematics. The set of natural numbers, as you have seen, as you have said just now, then the set of rational numbers, the set of reals, all these are examples of infinite sets. In some sense, n is the smallest infinite set and is called the countable set. And in what sense? You can actually think of naming its elements. You can actually think of, so in other sense, any countable set, you can actually think of naming all its elements, like A1, A2, A3, A4, where they are all, and AN and so forth, where they are all distinct. So this is kind of an intuitive notion of a countable set. And such a kind of infinity is generally expressed as, or the cardinality of the set of natural numbers is expressed as Aleph null. This is the symbol which is known as Aleph null. And we can say that the cardinality of A is Aleph null instead of, because that stands for the cardinality of countable sets. Okay. Any questions here? Of course, I have a question. Where the name Aleph came from? Why is it Aleph index with 0? Why is it? Why do we have such a name for the infinity, for the countable infinity? So, of course, there are many kind of debating issues regarding that, why it was named Aleph and things like that. But one view is that since null is the German of 0, there is something called a beginning of something. So from there null has come from, and Aleph, this was the name that was given by Cantor himself. And Aleph is the first letter of the Hebrew alphabet. Okay. So that is one story. There are some other stories as well. Interestingly, to digress a bit, I would, because we are talking about Aleph and null, I would also suggest you to look into this book, the El Aleph. Yoga it has nothing to do with mathematics, but still you can have it's found on the net, the English translation. He's an Argentinian writer, writing on mystic, fantasy, philosophy, lots of things. So this book has, of course, it's named El Aleph. It has to have the concept of infinity, and you can have a look at this book. Okay, coming back from this digression, let's consider the Hilbert's Hotel. Consider that you are the owner of a hotel having infinitely many rooms. And then one day you have infinitely many guests. No problem. You can put them there. Then one more guest comes in. What do? No problem. You just shift G1 to 2, G2 to 3, Gn to N1 plus 1 and so on. And you can put the first guest there. Now, there are infinitely many more guests come in. Once again, no problem. Just even and odd. First. So, all these kind of things you can do with this countable infinity. So, in this sense, in Galileo's words, paradoxes of the infinite arise only when we attempt with our finite minds to discuss the infinite, assigning to it those properties which we give to the finite and limited. Okay, now consider these. Let's do a little bit of example of arithmetic with this infinity. If you add Aleph null plus 1, it's actually Aleph null. It doesn't change. Or if you add Aleph null plus Aleph null, it still remains Aleph null. Okay. Now, let's look at some properties from where those kind of theorems come from. So, if A and B are countable, then A union B is also countable. If A and B are countable, then A cross Cartesian product of A and B is also countable. And if you have countable collection of countable sets, their union is also countable. By the way, to prove this, if you try to prove this, you will see that you will actually need countable axiom of choice. So, in any way. So, these are certain properties. And you can prove that the set of rational numbers is countable. Okay, you can also prove that. If you haven't done so, please try it out. Please try out all these results. They're not difficult at all, and you would have a feel of all these different kinds of countabilities. Now, as you all said, the real numbers is not countable, and you are all aware of this, of the proof that the real numbers are not countable. It's proved by contradiction. Suppose it's countable, and then you will get, if you have a countable thing, you take a number which is not equal to A1 in its first, if you have a decimal expression, you can enumerate them if it's countable, and then you can like have x1 which is not equal to this first point of A1, x2 not equal to the second point of A2, and so on and so forth. By the way, we are looking only at the 0, 1 closed interval, and show that even that is not countable, and of course R has to be uncountable. So now we have some way of having this countable infinity as well as something called this, an example of this uncountable infinity. By the way, this was again proved by, not by this method, this was proved in Cantor's paper. So before that, there was no concept of uncountable infinity. It was Cantor who first brought in, but he brought in a lot of things more, we will go into that. So anyway, the cardinality of the real numbers is called continuum and it's denoted by C. Now if we compare arbitrary sets, we say that, let's do a bit more formalism into this. We say two sets are equinumerous if there is a bijection between them. Okay, and we all know equinumerous sets have the same cardinality. And of course, a set is countable if it is equinumerous with n. Okay, that's sometimes taken as the definition as well for countable sets. Okay. And these are examples, open intervals A, B, C, D on the real line, they are all uncountable, R2, R3, Rn, they are all uncountable and they all have the cardinality C. One can prove this. Now, you can say that the cardinality of, take two sets, x and y, the cardinality of x is less equal to the cardinality of y if there is a 1-1 function f from x to y that is a bijection between x and some part of y. Okay, so cardinality of x is less equal to cardinality of y. And cardinality of x is less than cardinality of y if cardinality of x is less equal to cardinality of y, but cardinality of x is not equal to y, cardinality of y. So that's how we define the order relation between two cardinalities. And of course, we have that Aleph null is less than continuum. Aleph null is less than C. So one easy way to prove all these things, like to prove that the bijection is the Cantor-Schroeder-Bernstein theorem, which says that if the cardinality of x is less equal to y and cardinality of y is less equal to x, then cardinality of x is equal to cardinality of y. What is the importance of this theorem? Have all of you heard of this theorem before? No, this is the first time you are hearing. Okay. What is the importance of this theorem? So earlier, if you hadn't come across this theorem, whenever you were trying to give a bijection between two sets, you actually had to get a bijection between the sets. But now with this theorem, what you can do is, if you can have an injection from x to y and another injection from y to x, you already, by this theorem, you already get a bijection. So life becomes easy, rather proofs becomes easy. Okay, so that's the importance of this theorem. Now let's talk a bit about power sets. So if what is a power set, I'm sure you all know, just to recapitulate, if x is any set, we denote by Px the power set of x, that is the family of all subsets of x. Okay. Now say if x, the cardinality of x is n, the power set of x will contain 2 to the power n elements. Now of course, if you think of, you can say that if x has a cardinality kappa, because you now have countable cardinality and uncountable cardinality as well. Let's talk about them in general. So if x has cardinality kappa, then 2 to the power k denotes the cardinality of power set of x. Okay. So of course 2 to the power n is greater than n. So we have power set, cardinality of power set of x is greater than cardinality of x. No problem with that. Now comes this. Take any x, b infinite, finite, b infinite. Take its power set of x. You can actually prove that 2 to the power kappa is greater than kappa. What does this theorem means? Just think about it for a moment. Sorry, I didn't get you. Yeah, so earlier you all said that we had two kinds of infinities. One is the countable infinity and the uncountable infinity. So we had countable infinity, n, q, z, all these things, we had the countable size. And now we had r, which had the size of continuum, which is C, cardinality of C. Now you think of power set of R. You get another cardinality. Then you think of power set of that. So what you get is, there are infinitely many kinds of infinities. It's not countable and uncountable. There are infinitely many kinds of infinities. That's what the Cantor's theorem gives us. So the proof is also very interesting. So let us look into the proof. What we have? Of course, we have that cardinality of x is less equal to cardinality of px because we have an injective mapping. So each x, what would be that injective mapping? X going to the singleton set containing x, that will be your injective mapping. Now, we need to show that it is actually greater than. So how do we show that? We say that suppose they're equal, which means suppose there is a bijection G from x to power set of x. Now consider the set A. How is it defined? A is the set of all elements of x in capital X such that x is not in Gx. You can define a set. It may be empty, but you can define such a set. No problem of defining this set. Now, since G is a bijection, G is a surjection. Since G is a bijection, G is a surjection, so there has to be some x0 such that Gx0 is equal to A. A is equal to Gx0. Now x0 might be in A or x0 might be outside A. Now carefully see the construction. If x0 is in A, then x0 cannot be in A. And if x0 is not in A, then x0 has to be in A. So we arrive at a contradiction. So our original assumption was wrong because we have assumed that G is a bijection. Okay, that gives us this theorem, and that gives us this result that there are infinitely many cardinalities and there is no end to that. You can go on. Okay, so interestingly, there is some paintings are very similar to these ideas which are drawn by Escher. So let's give you this painting by Escher, who is very So this painting is famously known as drawing hands. Which has just look at it, which hand is drawing what? Which hand is drawing which hand? Okay, which hand is drawing which hand? So Escher has a lot of other paintings as well. You can have a look if you have not already looked into it. But there is a nice analogy with the kind of the mathematical proof that we have just given. Okay, good. So far so good. So hence we have that, we have Aleph null is less than 2 to the power Aleph null, less than 2 to the power 2 to the power Aleph null, and so on, and so on. So there are actually infinitely many kinds of infinity, and there is no set which is the biggest one. Okay. And one could actually show that the cardinality of continuum is equal to 2 to the power Aleph null. One could prove that. Once again, that proof I would leave you as exercise. You could have now with Cantor-Bernstein-Schroeder theorem, you could have that. You can define an injection from R to power set of n and power set of n to R, and you will get your result. Okay. So I won't go into the proof. Now I would like to go into something different. So this is all about counting. Of course, I'm sure I haven't done, but I'm sure that of course we can count to 1 to 100 quite easily, 1 to 1000 quite easily. I have not done that, but I am told that it takes more than 16 minutes, but surely we can do it. Okay. We can also think of counting 10 to the power 10 to the power 10. But can we count beyond infinity? Okay. Let's see. So we need also, again, for counting purposes, we need a special name. So again, historical, this is given the name omega, and let's stick to it. So we use the name omega for the counting purposes. So here what we have is that 0, 1, 2, 2019, dot, 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 and then omega, infinity, omega plus 1, omega plus 2, omega plus omega, and so on. We can think of that. So how could we think of that? So let's do things a bit formally now. Okay, so till now we have had the notion of cardinal numbers. Okay, we have all those cardinal numbers that Cantor introduced. What we are doing is that, can we think of course we can think of, because Cantor introduced that, but let's say, can we think of counting beyond infinity? Okay. Let's start with the definition of linearly ordered sets. We say that a set is linearly ordered by less than if it's irreflexive, transitive, and satisfies the law of trichotomy. Okay. R is linearly ordered by natural order. You can think of all words, let's say in English or any language, linearly ordered by the lexicographic order. Now, what are well-ordered sets? A set X is well-ordered if it is linearly ordered and every non-empty set, subset of it, has a least element. Okay, so a set is well-ordered if it is linearly ordered and every non-empty subset of it has a least element. Examples? You can prove that N is well-ordered. Okay, if you haven't. Partially ordered is that if it's reflexive, antisymmetric, and transitive. Okay, you need not have the law of trichotomy, that every element are related with each other, that you need not have. Okay? Okay. Now consider the interval 0, 1. That of course has a least element 0. But consider this set. 1, half, 1/3. Does it have a least element? No. So the set of, let's say, real numbers or the interval 0, 1 is not well ordered using the natural order. Using the natural order less than. Okay, that much we can see. Interestingly, since we have talked about axiom of choice, let me again mention that axiom of choice also means that you can prove from axiom of choice that every set can be well ordered. Okay, which means that even R doesn't have this natural order is not a well order. Axiom of choice, from axiom of choice you can say that it actually has a well order. There exists some order relation which well orders R. Okay, anyway, to continue. So two well-ordered sets are said to be isomorphic if there is a bijection and the structure preserving, which means that x1 is less than x2 if and only if fx1 is less than fx2. Okay, so these two are well-ordered sets are isomorphic. And then I introduce the concept of initial segments. I'm introducing a lot of concepts, but you can just listen to this and go back and think about it and look up something, and you will get, I'm sure you will get a hang of it, of all these things. If X is well ordered and A is in X, then the set X belonging to X such that X is less than A. Okay, you can define X is less than A because it's a linear order, no problem with that. Is called an initial segment of X given by A. X is well ordered, take any element A, take all the elements which are lower than A. That forms the initial segment of X given by A. Now one can show that X less than and Y less than, if these are two well ordered sets, then either they are isomorphic or one is an initial segment of the other. Okay, either they are isomorphic or one is an initial segment of the other. Okay, now think of the isomorphism relation. Okay, suppose it is W is isomorphic to W. Take W to be a well ordered set, W is isomorphic to W. W is isomorphic to W prime, this implies prime, and then the transitivity property also holds. That sense, of course, it forms an equivalence relation, but we also know, we can note here that we can think of some such W to be the type of W. To be, we mentioned some such set which has the, which are in the same equivalence class, which we could say that is the type of W, which is known as T of W, which means what? That if W is equivalent to W prime, then type of W will be equal to type of W prime. Where what is this relation? This is the relation of being isomorphic. Okay, as well ordered sets. So for any two well ordered set, okay, which are in this relation, their types are also the same. Okay, we can think of it. And such types are known as the ordinal numbers. These types give us the ordinal number. So the ordinal number is the ordered type of some well-ordered set. Once again, let me give you some examples, then it would be, I hope it would be more clear. So for example, 0 is the ordered type of the empty set. 1 is the ordered type of the set containing one element. 2 is the ordered type of the set containing two elements. N is the ordered type of the set containing n elements. Finitely, it's very nice and fine. So omega is equal to, some we also call it omega 0, is the ordered type of the countable set. 0, 1, 2 and so forth. And it doesn't end there. You can think of continuing. Okay, you're thinking all possible sets and all possible well-ordered sets. So omega 0, in fact, omega 0 is the ordered type of this set, which is basically the first least countable ordinal number. And omega 1 denotes the least uncountable ordinal. Okay, which means what? As I can say intuitively, we can think of omega to be the set 0, 1, 2, so on and so forth. And omega, what is omega 1? We just said omega 1 is the least uncountable ordinal, which means what? Whatever ordinal number which is less than omega 1, what will it be? It will be countable. Whatever ordinal number that is less than omega 1, it is countable. So omega 1, we can think of that 0, 1, 2, omega plus 1, alpha, which is the set of all order types of this finite as well as countable sets. Okay. So interestingly, you see omega and omega plus 1, their cardinalities are same. They are both countable sets. But what is different? The order. The orders are different. Okay, in that sense, they are different ordinal numbers. Okay, the cardinalities are same, but the orders are different. Okay, you can define it in some way. I'm not going into the exact definition, you can define it in some way. Just wanted to give you a feeling. So, let's look at the big picture about ordinal and cardinal numbers. An ordinal number alpha is a cardinal number if for every ordinal beta which is less than alpha, we have cardinality of beta less than cardinality of alpha. Okay, which means that omega 1 is a cardinal number as well as an ordinal number, but omega plus 1, omega plus omega, these are not cardinal numbers. 0, 1, 2 and so on, all finite numbers are cardinal numbers. Omega is a cardinal number because all less than that were finite numbers. All numbers less than omega. Then omega plus 1, omega plus omega, these are not cardinal numbers but ordinal numbers. So omega 1 is the next cardinal number denoted as, the next cardinal number is denoted as Aleph 1. Okay, and then omega 2 is the least order type of the set of cardinality greater than Aleph 1, and so on and so forth. So you can define this Aleph null, Aleph 1, Aleph 2. So these are all cardinal numbers. And in between these omega, omega plus 1 and so on, these are all ordinal numbers. And then comes n omega and so on, n omega plus 1, and again there is no end. Okay, so of course, as von Neumann says, in mathematics, you don't understand things, you just get used to them. Okay. Summing up, we have an exact list of cardinal numbers, Aleph null less than Aleph 1, infinite cardinal numbers, Aleph null less than Aleph 1, less than Aleph 2, and so on and so forth. If you remember earlier, we discussed another list of cardinal numbers, which also started from Aleph null, 2 to the power Aleph null, 2 to the power Aleph null, and so on and so forth. And we also considered C, which we showed to be equal to the, we didn't show it, I gave you as a homework, that C is equal to 2 to the power Aleph null. Okay. Finally, I would end, this is my last slide, so I will end today to talking about, okay, this is my penultimate slide. So talking about something which is known as the continuum hypothesis. What is that? So we have seen that Aleph 1 is the least cardinal greater than Aleph null, and C is the cardinality of the real line R. And of course it is not obvious at all that there is any relation between Aleph 1 and C. We could prove that C is equal to 2 to the power Aleph null, but it is not clear what is the relationship between C and Aleph 1. Now suppose if we assume C to be a cardinal number, not just the cardinality of the reals, then we can safely say that C is greater or equal to Aleph 1, because Aleph 1 is the least uncountable ordinal, the least uncountable cardinal in another sense. So we can safely say that C is greater or equal to Aleph 1 and the cardinals are linearly ordered. So Cantor conjectured in 1877 that C is in fact Aleph 1. So of course, when there is a conjecture, of course the question comes, is there a proof? Okay, when there's a conjecture, the next question, can we prove this conjecture? Is there a proof of this conjecture? So, in fact, before going into that, continuum hypothesis was actually the first problem in the Hilbert's list of problems in that 1900 Congress of Mathematics, International Congress of Mathematics. It was famous for this Hilbert's list of problems to be solved in the 20th century, and that this continuum hypothesis was the first problem in that list. And this was proposed and conjectured by Cantor. Now in 1938, Kurt Gödel proved that there is a model of set theory, okay, meaning there is a model of that Zermelo-Frankel, the set of axioms that we were talking about. There is a model in which all those axiom holds. What do you mean by a model? A model means it's a structure where all those axioms hold. Okay. So Kurt Gödel actually proved that there is a model where continuum hypothesis holds. Okay. And in 1963, Paul Cohen proved that there is a model of set theory where continuum hypothesis doesn't hold. What do you mean? So Gödel has a proof that there is a model of set theory where this C is equal to Aleph 1 does hold, and Cohen proved that there is a model where it doesn't hold. Okay, so means that it's not provable from the rest of the axioms of set theory. That's the basic knowledge that we get. Yeah. To end, this is more or less the end of my talk. To end, I will just leave you with two quotes. One quote is from David Hilbert. No one shall expel us from the paradise that Cantor has created. And as Cantor says, the essence of mathematics lies entirely in its freedom. Thank you.